All right, here we are again.
Professor, could I speak to you after class?
Sure.
Go.
Don't just remind me though before I click it off, because I might do that by accident.
Professor,
Yes.
since the midterm was uploaded over a day late, could we have like an extra day to do the midterm, like until Tuesday? That's what you did last time that you uploaded it late.
Oh, all right. Okay. You can have
It's
it. You're
okay
right.
if you-
I did forget, and you're absolutely correct. All right.
It's
Tuesday
okay.
it is.
I was just checking.
If you need it, if you definitely need
Yeah,
it.
I probably won't need it, but just in case I wanted to confirm.
All right. You're right. I did forget for a full day.
It's okay.
So yes, that's fine. All right. All right. So anyway, so here, where are we? Oh, chapter 11. Yes, 11. We're not quite done with it. We still have a little ways to go. We saved one of the more complex topics for last, and so we're going to look at this. Yeah, but you know what? Noah convinced me you can have till Tuesday if you want, because yeah, I delayed. I forgot to post it the last time we met, so you can have that extra day if you need it. It's all right. So anyway, so if anyone else doesn't have it done yet, yeah, if you need it, you know, Tuesday is fine too. All right. So anyway, so yes, chapter 11, conditional probabilities. This is what we've been saving for last. This is our build up to the multiplication rule. So we've already briefly reviewed. Let's actually go back and quickly remind ourselves what we've been covering in this section of the chapter. We've been introducing a few new types of probabilities that we will need in order to understand what conditional probabilities are and how they are used to create the multiplication rule. So we started out with, well, first we introduced the table, the joint probability table. If you recall, we have students that are majoring either in finance, accounting, or marketing, and some of them are getting a bachelor's degree and some of them are getting an MBA. So we've got all the information right here. And we were able to calculate two basic types of probabilities. First, we were introduced to joint probabilities, which are the probability that two things are true. And they can be easily calculated directly from this table. For example, we calculated the probability that a randomly chosen student is getting their bachelor's degree in finance. How do we know this? Well, we look at the intersection of the row for bachelor's degree and the column for finance, and we find that 130 students in this business school are getting their degrees, their bachelor's degrees in finance out of 500 total. So therefore, all we have to do is take the ratio of those two numbers, 130 out of 500, and we're left with 26%. Now, this logic is based on the assumption that everybody is equally likely to be chosen. I just want to mention that. If not, then we have to do something much more complicated. But we're literally just randomly picking somebody out of this population, and we're saying, all right, what's the likelihood that the person I is a bachelor's degree student who's studying finance? Now, all the joint probabilities can be done in exactly the same way. For example, if I wanted to know the probability of somebody's getting an MBA in, let's say, accounting, and we did this exact same example, I would have 35 out of 500, okay? Because all I'm doing is counting up how many people fall into that category out of the total amount of students in the business school. So the joint probabilities are very straightforward. Yeah, here it is. We definitely did this example. The probability that a randomly chosen student is getting their MBA in accounting is simply 35 out of 500, or you can rewrite that as 7%. All right, now what else did we cover? We also introduced what are called marginal or unconditional probabilities. And that means basically what I'm looking for is either a column total or a row total. For example, here, if I just say I want to pick somebody, or I'm picking somebody, and I want to know the probability that they're getting a bachelor's degree, regardless of their major, then what I need to do is consider the total of all bachelor's degree students, which is 400, divided by the grand total of 500, which is 0.8, or 80%. There's an 80% chance that if I randomly pick somebody, they're getting their bachelor's degree. So this is called a marginal or unconditional probability. And we can do the same thing with the majors. For example, we asked here, what's the probability that a randomly chosen student is getting a degree in accounting, regardless of what level they're at? Okay, so this turned out to be 215 out of 500, and that ratio is 0.43 or 43%. Well, now, what other kinds of probabilities could we calculate then besides these joint probabilities and these unconditional probabilities? Well, we've saved that one for today because it's a fairly complicated idea. Oh, one more thing we did. We also introduced a different version of this table where all of the numbers in the original table were divided by the total number in the entire table of 500, so that now each of these numbers is actually a probability rather than a raw total. And the reason for doing this is because sometimes if you're only interested in the probabilities rather than the actual numbers, then this is all you need right here. And this might be a quicker way of calculating the probabilities that you're interested in. All right, so finally, we get to the most complicated of the new probabilities, which is conditional probabilities. So what's happening here is that the event that we're interested in, its probability depends on whether or not another event is true. That's the complicating feature here. We've got two events that are related to each other somehow, whereas the probability of one depends on the probability of the other one. So we're going to introduce the concept of the conditional probability, but we're also going to see that the formula that we need is pretty straightforward. It's based on what we've just been doing. In other words, it will require a joint probability and an unconditional probability. But we know how to calculate those, and that's why this one gets saved for last. Otherwise, it would have made no sense to you whatsoever if we started with this one. So let's see, here's an example. And you'll see the wording is a little bit different. So we have to be very careful with this wording. What exactly are they telling us? Suppose that I say this: the probability that a randomly chosen student is majoring in marketing, and this is the new part, given that he or she is pursuing a bachelor's degree. What I'm saying here is that we already know that this is a bachelor's degree student. And with that information, we now would like to calculate the probability that this person is getting their degree in marketing. So we need to create a new type of notation for this. And you can see we've got this line here, which in English is pronounced given that. So in other words, the first event T is what we're trying to figure out the probability of. The second one, this B, is the information that we've already been given. So up at the top here, you can see that the way this is written, we know already that this is somebody who's getting a bachelor's degree, not an MBA. We already know that it's not an MBA student. And that means we can now figure out the probability that they're getting a marketing degree. And so what we need to do is introduce the formula that we'll use from now on to calculate these conditional probabilities. It's always the same. We need two pieces of information. Okay, now we have the ratio of, in the numerator, we have the joint probability of T and B. And down here we have the unconditional probability of B. So all of these conditional probabilities will be done in the same way. Oh, one more thing, this B, because this is the information we have, We sometimes call it the conditioning event. You don't have to remember that, but I just want to mention that's the probability that always goes into the denominator. Okay, the numerator is just the joint probability between T and B. The denominator is the probability of this conditioning event, or B in this case. Now, both of those we can calculate directly from the table, and then the ratio of those two probabilities is what we're looking for. Okay. Now, let's see how that's done. So if you go to the table, and I've repeated the information we need up here, T given B, this probability is equal to the ratio of the probability of B and T over the probability of B. So look how easy it is to figure this out. This is the probability of B and T. And this is the probability of B. So the ratio of those two is our final answer, which is right here. It's getting lost in all this shuffle here, but oh yeah, 225, because that's the ratio of 0.18 over 0.8. So once we know for a fact that this is a bachelor's degree student, the probability that they're getting their degree in marketing is 0.18 out of 0.80, which turns out to be 22.5%. Now, I did point out in the bottom left-hand corner, I threw in a little detail on the side here. The probability of just plain T, the unconditional probability of T is right here at 0.22. And if you notice, it's different than what we just calculated. All right, so in other words, knowing that the student is a bachelor's degree student changes the probability that they're studying marketing. And that's because the proportion of students who are studying marketing is different among the bachelor students and the master students. That's why the probabilities here are different. So knowing that this student is studying or getting their bachelor's degree affects the probability that they're majoring in marketing because they're different. All right, so I just want to point that out. So in fact, these are two different probabilities.
The number like highlighted in blue with the circle, that's the total, right? That would be like 0.18 divided by 0.80.
Yes, right. I put it there because I ran out of space.
Okay, that's okay.
And then I highlighted it so you could see it among all this mess here. All right, yes, that's exactly right. 0.18 over 0.80 is 0.225. So let's do another one. Oh, by the way, it's written out on this slide anyway, but I just wanted you to see it. It sometimes is very helpful to see it all in one place. Here, I've just written it out separately so that you can tell, what that probability is supposed to be. All right, so let's do another one. With this kind of stuff, the more practice you have, the better. How about this one? The probability that a randomly chosen student is pursuing an MBA, given that he or she is majoring in accounting. Now, this time, the information that we are providing is the fact that this person is studying accounting. That's why that goes here after the given that sign or symbol. Don't forget, this is given that. So what do we know? We already know that this student is getting their degree in accounting. With that information, we now should be able to figure out the probability that they're getting their MBA. So just like before, we've got in the numerator, the joint probability of these two events. And in the denominator, we have the probability of this event because we know that this is true. And so now all that remains is to go back to the table and look up these two values and then calculate the ratio. Okay. Yes. So you can see it's turning out not to be that terribly complicated after all, but only because we have already been introduced to these other two types of probabilities. All right. So let's do this with the table. So I've got everything together in one place. So the probability of n given A, I've rewritten the definition right here. And you can see this 0.07 is the probability of M and A. And down here, this is the probability of A. So you're just looking for the ratio of 0.07 to 0.43, which is approximately equal to 0.1628. And once again, in the bottom, I've also noted that the unconditional probability of M is 0.20, and they're different from each other because the proportion of students who are studying accounting is different between the MBAs and the bachelor's degrees. All right, one more. What's the probability that a student is majoring in finance given that he or she is an MBA student? So this time the information we were given is the M for MBA. With that information, we'd like to know the probability that the student is studying finance. So, and here you can see, here is the probability of F and M. And here's the probability of M. So we're just simply looking for that ratio, 0.09 to 0.20. And that turns out to be 45%. And again, I'll put it down here, but the probability of F, just plain F, is actually 0.35, which is different than this probability. And the reason why they're different is because a larger percentage of the MBA students are studying finance than among the bachelor's degree students. All right, then. With all that being said, we're now finally ready to introduce the dreaded multiplication rule. All right. So the rule itself is based on joint probabilities, as it turns out, but it's defined in terms of conditional probabilities. So what do I mean by that? Well, it turns out, first let me show it to you. There's actually two equivalent versions of the multiplication rule. Either one can be used depending on what information you have. So for example, this is the first version of it. So you can see it's defined as the probability of a joint probability, actually, B and A. Remember, this is the intersection symbol and it represents and. And here we go. Look, we have to multiply the conditional probability of B given A times the probability of A to come up with this result. So this is why it took so long to build up to this rule, because we needed to understand what conditional probabilities are all about. So what about the equivalent version? I'm actually going to put them both in the next slide so you can see them together side by side, but you'll see that they're very similar, but there are important differences. All right, so the second version down here, you can see, is not exactly the same as the first version up here on top. Okay, so this is the second version, and you can see what's changed is the order of these letters. In other words, here we have A given B times the probability of B, and both of these, though, will give you the same results. But under some conditions, one of them may be more convenient than the other. It depends on what you're doing. So it's good to know that there's two versions of this rule that can be used. It's like having, I don't know, it's like having a second car. You know, you got your main car and then you've got the backup one in case something goes wrong with your main car. So now all that remains to be done is to do some examples. And we'll get ourselves some serious practice here. All right, imagine the following situation. I'm choosing a card from a deck. Now, the events that I defined are A, the card is an ace, and B is the event that the card is black. Now, these probabilities you can see because there's 4 aces in the deck. The probability of choosing an ace is, of course, 4 out of 52, which can be simplified to 1/13. Because there are 26 black cards in the deck, that probability is 26 out of 52, which is a half. Now, here's the interesting question. What if I'm interested in the probability that both of them are true? Not just A, not just B, but both. Ooh, that changes everything because now all of a sudden we're looking at a joint probability, which makes it a candidate for the multiplication rule. So we're going to actually use both versions of the rule to come up with this probability. All right, let's start. Let's just randomly pick the first one. We'll do this one first. So if we're going to use this approach, we have to calculate 2 different probabilities, the probability of B given A and the probability of A. All right, now, since the deck contains 52 cards, A by itself is easy. We've already determined this to be 1 out of 13. Okay, this is the tricky one, B given A. Now, how do we interpret that? Well, what this is telling us is that we know for a fact that the card we chose is an ace. Okay, that's the given information. What's the probability then that it's black? Okay, so in other words, we are already informed that we picked an ace, and if you recall, there were actually 2 red aces and 2 black aces. So therefore, the probability that it's black, given that we know that it's an ace, is 1/2 or 2/4. All right, so we got the 4 aces in front of us, 2 of them are black. The probability, therefore, of a black ace, given that you have an ace, is 1 out of 2 or 2 out of 4. All right, now we have everything we need to know to bring these together and solve for our probability. Watch this. So there's the version of the rule that we're using, and we've already seen that this probability is 1/2. This probability is 1/13. Their product is therefore 1 out of 26, and that is approximately equal to 0.0385 or 3.85%.
Why is it more advantageous, I guess, to use this formula over the other one?
Oh, in this case, it's not. Both of them are equally advantageous. We're going to show the second one as well. So let's do that right now. So here, it doesn't actually matter. So now the only thing we have to do differently is we need to figure out these 2 probabilities. So B is easy. It's 1/2 because 26 out of the 52 cards are black. That's a breeze. What about this one, though? A given B, what does that even mean? It means you know for a fact that the card is black. And you also know that among the 26 black cards, 2 are aces. So this probability is 2 out of 26 or 1/13. So once you know that it's a black card, the chances that you chose an ace becomes 2 out of 26 or 1 out of 13. So once again, we substitute these back into the equation. And guess what we're going to find out? It's the same. It has to be the same. And so you see, if you plug them in, you will in fact get, again, 126 or 0.0385. Okay, now in this very simple example, it turns out that we didn't even really need to use the multiplication rule. Why not? Because remember, what are we being asked to do? B and A means a black ace. What we could have done instead, given our knowledge of the deck, is that we could have said, well, you know, there are 2 black aces in the entire deck. Therefore, the probability of choosing one of them is 2 out of 52 or 1 out of 26, which again comes down to 3.85%. So in this example, the multiplication rule wasn't really necessary, but at least this way we can double check our results, which is kind of nice. So, you know, like any other branch of math, typically any problem can be solved in more than one way. Now, you might recall that with the addition rule, we had the full version of the rule, and we had a special case. Let's just quickly remind ourselves what that was all about. With the addition rule, we're looking at the probability of a union. And let's see, where is that? Here it is. So this is our addition rule, which you recall. But you remember there's a special case when we can use a simpler version of it. And that would be, the simpler version looks like this. But who remembers what has to be true for us to use this rule? A and B have to be
Mutually exclusive.
That's it, exactly. Now, with the multiplication rule, there's also a simpler version available to us, but it's not based on mutually exclusive events. It's something completely different, which is called independent events. This is a very different idea. Now, you know what the word independent, you see it all the time. It basically means that the 2 events do not depend on each other. So I'm going to show you a quick example of this in a second. So intuitively, you'll be able to get a sense of what does it mean for events to be independent. It essentially means that if one occurs, it does not affect the outcome of the other one. And if 2 events are independent, then we'll have a nice, simple version of the multiplication rule available to us. All right, so here's 2 events. Let's see, what do you think? Are these independent? A is the event that John gets an A in Math 1060. B is the event that the weather is unusually cold. So what do you think, independent or not independent?
I think they're independent.
Absolutely, because there's no reason why his grade should depend on the weather. So this would be an example of where 2 events are independent of each other. Okay, so John's grade does not depend on the weather, and the weather does not depend on his grade. Therefore, these are independent events. Okay, now, on the other hand, if the second event had been John studies 20 hours a week, well, then they're clearly not independent, are they? No, because one clearly influences the other. But here they're completely independent because one does not affect the other. Now, let me show you another way in which events can be independent. This is an interesting case because we're going back to the deck of cards and we're doing something a little different with them. what we're doing is saying, all right, we're picking a card from a deck. We look at the card, we put it back in the deck, and then we pick another card. The events will be defined as A is that the first card is red, and B is that the second card is red. Now, because I'm putting the first card back, that means that when I pick the second card, the entire deck is still intact. And so therefore, the chances of getting a red on the second card is not influenced by what happened on the first card. That means that these events are independent of each other. All right, so I want to illustrate this with a diagram. It's kind of a simplistic diagram, but what this is supposed to represent is here's the deck on the left. We pick a card and we look at it. That card gets put back in, and maybe the deck is shuffled too. Then we pick another card. Okay, so I hope the diagram sort of says what's going on here. After the first card, we put it back, and then we shuffle, and then we take another card. So we call this technically, and you don't have to remember this, but it's technically known as sampling with replacement. And it implies that the outcome of the second draw does not depend on the first draw. Because again, the entire deck is intact when we pick the second card. So that's what just happened here with our experiment here. We've got two cards, but we picked one, put the card back, and picked another one. Now, what other possibility is there? Well, how about this case? We pick the first card, and then we don't put it back. And then we pick the second card. This is called sampling without replacement. And now, all of a sudden, what happened on the first card affects what happens on the second card. Because now, if the first card is red, when I go to pick the second card, there's only 25 red cards left. So the probabilities on the two draws do depend on each other. So this is very different than a roulette wheel, let's say. With a roulette wheel, every spin is independent of all the other spins. But here, if I'm picking the cards one at a time without putting them back, then the second card, the outcome of the second card depends on the first card, and they're no longer independent of each other. All right, so what's then, using the first case, what's the probability that both cards are red? In other words, we're drawing with replacement. And so I want to know the probability that both cards are red. All right, so we're going to use the multiplication rule. But we're going to notice something very interesting as we go along. So the probability of A is a half, of course, because there's 26 red cards in the deck. How about B given A? Well, that's the interesting part. The probability of B is the same. Now, remember, we put the first card back. So the probability of B is a half, whether or not the first card was red. Again, because the entire deck is intact when we pick the second card. So when we plug these numbers into our multiplication rule, you'll see that we wind up with, very simply, a quarter. A half times a half is a quarter. And the key to the whole thing is right here. By putting the card back, these two probabilities are the same, which is 1/2. Now, we can, in a position now to formally define what it means for events to be independent. The case with John and the weather, that was pretty intuitively clear, but we need to have a much more formal definition of what it means for events to be independent. And they'll be defined in terms of conditional probabilities. So in order for events to be independent, two things will be true. What are those two things? The probability of B given A is just the same as B by itself. In other words, knowing that A is true, let me add this here, knowing that A is true does not affect the probability of B. And we can say that in the opposite direction as well. Okay, in other words, in the second case, knowing that B is true does not affect the probability of A. Now, both of these have to be true. One of them is not enough. Okay, independence implies that both of these conditions are met. It's like with the example of John and the weather. Knowing that the weather is cold does not affect the likelihood that he gets an A, and knowing that he got an A does not affect the likelihood of it being cold. All right, now, with all this being said, if this is true, if A and B are independent, we can now create or define our simplified multiplication rule. And when you see it, you'll be very happy to see that it is simple indeed. Very simple. How simple is it? Watch this. Okay, so these are the two different versions of it. Now all of a sudden, look how easy this is. The probability of B and A equals the probability of B times A, or equivalently, the probability of A times B. It's so easy. We like this one. Easy is always better, don't you agree? Yes, we do. We like easy or simple, especially when it comes to math. All right, now, here's another simple example. It's related to the cards case, except it's a little different. This time we're going to flip a coin. Now, it should be pretty clear that when you flip a coin, let's say I flip the coin twice, and I'm only interested in whether it turns up heads or not. Does the first flip affect the second flip? No. Every time I flip the coin, I'm starting all over again. The probability of getting ahead is always 1/2. So what I want to know is the probability that they're both heads. This is clearly a joint probability, but I want to use the simplified version of the probability multiplication rule because they're clearly independent of each other. So watch how simple this is. I'm using the probability B and A, both are heads, is the probability B times A. And again, because they're independent, each one has a probability of 1/2. And so the total is 1/4. There's a 1 out of 4 chance of getting both heads. Now, I just want to remind you of something else. We previously used this example, just as a quick review, a reminder. In the case that a die was rolled twice, the sample space consisted of the outcomes and you might remember we said many times that each of these is equally likely to occur. Well, now we're in a position to prove it. So imagine, so our experiment consists of rolling a die twice. Suppose that I define, or suppose that the following events are defined. Equals the first roll is even. B is the event that the second roll is even. So the probability of getting 2 consecutive evens can be calculated with our simplified multiplication rule because clearly the rolls are independent of each other. Okay, since the rolls, or actually let's put it this way, what is the probability that both rolls are even? Okay, so we can use, because the rolls are independent of each other, we can use the simplified multiplication rule as follows. Now, just by a ridiculous coincidence, it's exactly the same as the heads and tails. So I'm going to just borrow that formula from back here. So this shows now remember, this corresponds to EE. Okay, in other words, B and A in this context means 2 consecutive evens, which we were calling previously EE. Okay, so this is why the probability of EE is 1/4, because the rolls are independent of each other, and we can therefore simply multiply the probabilities of getting an even on the first roll by the probability of the second roll being even. And so similarly, based on the exact same logic, we can use the simplified multiplication rule to show that. And then we did all the others in exactly the same way. The O must be a quarter, OE must be a quarter, and OO is a quarter. So before we stated it many times, but this is a formal proof that each of those roles is equally likely to occur, and therefore they must all be a quarter. All right. Ooh, that was a lot. So now we're actually done with chapter 11. Chapter 11 is our introduction to probability theory, which is pretty abstract to a certain degree. The calculations aren't that difficult, but conceptually it's a little bit on the difficult side. It takes a while to get used to these concepts. What comes up in chapter 12 is our introduction to statistics, which is a little bit different because there it's more focused on formulas. And so conceptually it's not hard to follow, but the actual calculations can be much more challenging. So I don't know what you prefer, but in 12 we'll be doing a lot of work with our calculators. And of course, probability theory is the foundation of statistics. That's why we normally teach probability theory first, to get you used to what's coming up in statistics class. Now, statistics is a very important branch of mathematics, and the reason why is because it's useful. Everything in statistics is meant to be useful, not theoretically elegant necessarily, but useful. There are a lot of branches of mathematics where the only purpose is elegance, theories, proofs, the whole 9 yards. Whether they're useful or not is irrelevant. With statistics, it's the other way around. Nothing gets into statistics unless it's useful. So it shows up in a lot of areas, which we'll discuss later on. Now, as it turns out, just by lucky coincidence, I have some interesting videos for you to see before we actually look at chapter 12. Now, the first two, if you can believe it, are actually funny. It's hard to imagine making statistics funny. But the comedian in these two videos actually managed to do exactly that. So we're going to start with the first one. And I'm sure you'll like this one. You'll see what I mean when we get to it. And this is a comedian who specializes in making comedy about technical areas because he's an engineer by training. All right, so let's check this one out. I'll fire it right over there, and I think you will like it very much. All right.
Professor, I think you're muted. Professor,
Yeah,
you're
you're
muted.
muted. You're muted.
Ah, there we go. Thank you for reminding me. So yes, let's try that again. So I hope you all like that. It was a lot of fun. And now the next one that we're going to see is actually not based on math at all. It's the same comedian, but he put this very interesting bit together about PowerPoint. Now, of course, all of our slides are on PowerPoint, but I think since we have a little extra time here, and this is so much fun, I think it's worth our while to watch it, because what he's essentially doing is explaining how not to do a bad PowerPoint presentation. And it's just fun. If you're not using PowerPoint, it may not mean as much to you, but I'm sure you've been in classes with PowerPoint presentations, not just this class. And sometimes, it's easy to make it, let's say, not interesting, not easy to follow. It's kind of an art to make useful and helpful PowerPoint slides. So anyway, but he's going to talk about it, and his message is very serious. I mean, he really is trying to help you. Oh, is there such a thing as Google Slides? I wouldn't know.
Google Slides is the superior PowerPoint. It's by Google. It's on Google. It's part of the Google Drive suite, and it's amazing.
Wow, I'm glad you told me, because I had no idea.
Beautiful.
I'm so far behind the curve. It's so awful.
It's
If
okay.
I'm getting further behind, I think. My knowledge of all things technological is pretty limited, so I'm not surprised to hear this. Uh, but anyway, let's take a look. But the principles are the same, whether it's Google Slides or PowerPoint. So let me fire this over there. Okay, here it is. This will be fun. All right. Well, that was kind of, just a fun little detour there. But I think you'll agree that you may have seen some dreadful PowerPoint presentations, and he's kind of trying to help you through all that. But a lot of those were fun, like the cake chart and all that good stuff. Yeah, yeah, yeah. He's pretty interesting. Anyway, so now we're ready to see a video that actually has something to do with statistics. So this is meant to be a broad overview of what statistics is all about. It's not too terribly technical. There's a few things that they'll talk about that we haven't discussed yet, of course, because we haven't started. But I think it's a good place to get started to understand what we're trying to accomplish in the field of statistics. So I like this video a lot because it covers a lot of useful territory in a very painless way. Right, and it does the opposite of what he's talking about here. They do a nice job with the graphics, and they don't overpower you with information. So it's and the animations are just exactly how much they need. So based on what he was saying, this presentation we're about to look at is a very good one. Okay, well, it's actually a video. It's not a presentation, but still, it's a very good one. All right, hold on one second. Let me get that thing out. Here it is. Okay. All right, let's check this out. All right. Well, it was kind of long, but we're going to cover all those topics as we go along. But right now, since there's just a very few minutes left, I just want to introduce one quick topic from this chapter that sort of leads the way to where we're going. We're going to just introduce one very important distinction that will be made in this chapter 12. We're going to distinguish between what's called a population and a sample. Now, you've heard those words before, and you probably have a pretty good idea of what they mean. But in statistics, we don't normally use the word population to represent a group of people, but instead, what we're interested in is measurements or numbers or something that describes the characteristics of people rather than the people themselves. For example, we may be interested in studying their ages or their heights or their weights or their incomes or how far they drive to get to work. That kind of thing is what we might be studying. And so the population is a collection of interests, measurements or outcomes of interest. A sample is what we will call a subset of that population. And the point of all this, as we'll see in a minute, is that the sample is the one we're actually going to use most of the time because it often is very time consuming and costly to analyze all the elements of a population. Often a sample will do the job just as well as long as we choose it carefully. For example, what if the US government wants to determine if the average age of Americans is higher than it was 20 years ago? If so, changes will be made to the Social Security system because, let's face it, it's always on the verge of running out of money. So the age is going up, they will have to figure out a way to finance it. Now, they could do one of two things. They could literally go through every single person's records and see what their ages are. But guess what? That's a lot of people, 330 plus million people. That's a lot of ages to analyze. Is it really necessary to go through every single one of them? Well, as it turns out, the answer is probably not. Because, of course, this would take forever. And if we choose a sample of Americans instead and analyze their ages, that will probably give us a very good idea of what the average age of the entire country is. Now, here's the thing, though. We have to be careful about how we pick the sample. Otherwise, this would be a terrible mistake. So we're choosing a smaller group of people, and it could be much smaller in this case, because again, if you have such a large country, it might be enough to pick a sample of, let's say, 100,000 people and look at their ages instead of the entire country. Now, the bottom line, though, is that you must pick the sample carefully. In this case, we literally will randomly pick numbers or names for people scattered all across the country. And if we pick the sample in such a way that it really and truly reflects the population, the average age in our sample will end up being very close to the average age of the entire country. That's all we need. All right. Now, here's the opposite case. What if we accidentally picked only retired people? Would that give us a good reflection of the entire country? No, of course not.
Oh,
What if? Absolutely not, because the average age among the retirees is much higher than the average. Or what if we went to the other extreme? We accidentally picked only 100,000 college students. Again, that will not give us a good reflection of the entire population. So this will work well as long as we choose carefully. Now, I came up with a marketing example. Now, you know perfectly well that marketing is the art of selling products to people. But how do companies know what people want? Well, they take surveys, or sometimes they'll give out free samples. Like, imagine the following scenario. Coca-Cola has spent a lot of money developing a new flavor, pumpkin Coke. Okay, now they want to know if people are likely to buy it. So what they could do is visit every single person in the country and ask their opinion about the pumpkin Coke. And they'll get a very accurate result. But how long would that take? Forever. It would be very expensive. So do they really need to do this? No. So what might they do instead? What if they show up at the local supermarket with samples of pumpkin Coke, and everybody who walks by gets a cup of the new pumpkin Coke, and they're asked whether they like it or not? Could that be done? Of course it could. Would that give them a lot of useful information about how likely it is that the entire country will like the pumpkin Coke? Yes, as long as they do this properly. Now, of course, there are companies who specialize in doing this kind of thing. They get a hold of people and ask their opinions. They know how to choose these samples in a very accurate way. So Coca-Cola most likely would hire one of these marketing companies to do this, but they could just go ahead and set up stands in supermarkets and offer the free product to people who are walking by. They don't do that as much as they used to, but it is a valid way of getting information about the entire population without having to actually contact every single person who lives in the United States. So the bottom line here is that we'll spend a lot of time discussing the distinction between populations and samples in this class, in this chapter, I mean. All right, anyway, so I think that's all I wanted to do with this chapter right now. So here's what we need to do. Why don't you finish up your second midterm over the weekend, and then when we meet up again on Monday, we'll just dive ahead into chapter 12 and learn more about statistics, okay? And be prepared to do a lot of calculations. All right, this is a very calculation intensive chapter, but the formulas, they just take a little getting used to, that's all. All right, so other than that, I guess we're done. So I'll just wish you all a happy weekend. Okay.
Bye.
See
All
you
right.
later. Bye.
Thank you.
Thank you. Have a good weekend.
Okay, bye.
Course, he already claimed.
Okay,
a lot of
so
loss,
I'm really,
which
really nervous
marks
about my
the
math
right to
midterm, which
the
makes
second
no
half.
sense
And
because
it's
I was
not a
getting everything
situation
right
where
in
we
class
can
and
just say,
I
"Oh,
feel like I did it right, but I'm like, I'm really, really, really nervous. So
We can't either.
You mean the second one?
this second one, not the first one, from was fine, but the second one, I'm
First
really
one
scared.
was great.
Yeah, I'm
So
really scared.
you're worried about the second one, really? Why?
I don't know. I don't know what to do though, because if I don't do well, because I don't know what I should do.
Respond back to the email.
Well, I mean, you really did great on the first one.
Yeah,
Okay.
so maybe that's a sign I will do
No
well.
problem.
I think you're underestimating yourself with this stuff.
Okay.
All you have to do, make sure read each one carefully, go through the slides, and make sure you can figure out which kind of problem it is. In other words, are you asked to calculate a simple interest problem, or is it an annuity problem, or maybe is it a compound interest problem? Once you figure out which one it is, then you just plug numbers into the formulas.
Yeah,
Um,
I think I did that pretty successfully. I think so.
Yeah.
So,
I really think you're probably understanding it better than you realize.
okay, maybe. I hope so.
This was September.
So yeah, and now if you really and truly get stuck on something, like let's say question 8 is completely baffling, you can send me an email over the weekend and I'll try to help you with it.
I mean, okay. Questions. Okay. Questions question one, and question. Well, question. Actually, maybe not question one, but question 2 was completely baffling. I was really
All
confused.
right, let me look at it real fast. Just to see what the issue is. You mean this one with Eileen?
Yeah, with Eileen. Yeah.
Who cares? No one's
All right, well, this is this is one of those cases where it's compounded monthly. So you need to calculate the future value of the sum using that formula with A in it. Remember?
Yeah, the AP.
Right, that one.
A
Yes.
AP plus R over N NT.
That one, yes, exactly. Once you have that part figured out, you can figure out how much interest she paid. Because if you know, let's say the future value is 50,000. She's only borrowed 40,000. That means she must have paid $10,000 worth of interest. Okay. Now the simple interest is easy. That's the I equals PRT formula.
Yeah, that I could figure out, that I could do.
Okay. So the compound interest is just the difference between the total and the simple interest.
That's what I did. Okay.
Okay, well then you're all set.
Great, wonderful. Okay, so just to make sure, I use the I determine the future value of a sum when they're only doing it once. And I
That's
do,
right. Yep.
and I do the A bracket R squiggly do, all that stuff when they're paying it more than once.
That's right, exactly.
Thank you for knowing what I meant by squiggly do.
Yes, I got it. I get it. Yes, I understand. So
Okay,
you're absolutely right. That's reserved for cases when the payment is more than once.
Yeah. Okay, great. Okay,
Is that
thank
it?
you.
Okay, sure. And again, if you get stuck, just send me an email.
Thank you.
All right.
Bye.
Okay, bye.